the read table function to import Excel file. So here I install a package and read Excel and use library function to activate it. And then you use the function read Excel to select the data we need and then save the fish density in the fish density and the copper density in the copper density. So the first part of this question is to using norm theory to calculate the mean and the standard of mean. And the main part is quite easy. We can just use the main function in the R language. And the standard error part, we can use the formula that we learned from the class, which is using the standard error function in R and divided by square root of the level of fish density and the coal density. And then print the result like this. And then for the second part of this question, we need to use the bootstrap samples to calculate the mean and standard error of mean. So here, I fill out a function that called bootstrap. In this function, I want to choose one sample of data randomly. So here, I use the floor and R uniform to set the index randomly, and then save each of the corresponding data to C and return C. And because of the previous bootstrap, the result of previous bootstrap function, there will be a matrix with each of the column is a sample. So we need to calculate each of the columns mean and the median in the following question. So here I build out the two functions for mean. One of them is mean of a column and the other one is the median of a column. And then to calculate the standard error more easily, I build out the standard error to calculate function as well. And this function can also calculate the standard error of bootstrap and the jackknife as well too. Because of the different formula of calculating the standard error mean in bootstrap and jackknife. So here I add two judgment parameter in this function, which is BT means bootstrap and the JK means jackknife. If the BT is true, the function will return the formula of bootstrap error standard error of mean. And if the JK is true, the function will return the formula of the standard error of the jackknife.
So what is S here? In this function, what is X?
X. Oh, X is the previous that we can using the mean function or the median function to get a set of each of columns mean and the median. And then
so X is a vector.
Yeah, it's a vector.
It's a vector that store all the 1000 bootstrap mean.
Yeah, it is.
You use the same X, so it confused me. It's okay.
Oh, okay. Then we can back to our questions. So to calculate the mean of bootstrap feature copper, we can just use the bootstrap function that I just built and use main function to calculate each of the mean of each column, each sample, and then mean each of the columns mean just like this and print the result. And the standard error is quite easy as well, which is that the BT is true. Okay, this is I apply the histogram of mean of fish density and the copper bar density. Okay, this is question 2. In this question, we need to compute the median and the bootstrap standard error of median for fish and copper bar density and apply the histogram. In this question, we can do it easily with the function that we just built. So here, like using Bootstrap to sample data, sample data 1,000 times, and using median function to get a median of each sample, and then make the each of the sample and print the result. And the standard error part, which is set the BT parameter is true, and print the result. And then this is the quality histogram of median of each density and the cohort density. Okay, let's move on to the question 3. In this question, we need to plot fish as the dependent variable versus the cohort as an independent variable. And then we need to calculate the regression coefficient for the base. In the base is the intercept is beta 0, the slope is the beta 1, and calculate the bootstrap and the arrow for beta 0 and the beta 1 and plot the histogram. So here I set out two functions. One of them is to calculate the product of two metrics. In this function, I built out three layers of for loop, and then calculate the product of two metrics. And then the other one is the function of b of calculate the regression coefficient. And using the formula is like the b equal to this is the function formula that we learned from the last lecture. So we can use these two functions to solve this problem. And in this, you calculate the regression coefficient. So here, so you need to pair the data with, you need to sample the data with pairs. So you cannot use the bootstrap that I built in the question 1. So here, I back to using the floor and the R uniform function, and sampling the index, and say the code density corresponding to the A index to BT code, and do the same to fish density as well, and use the regression B function to calculate the regression coefficient easily. And then mean that each of columns regression coefficient and print the result. And the standard error, I can use the standard error function that I built with the BT converge to true. And then I get the two number, which is beta 0 and one is beta 1. And the beta 0 can be the intercept of the regression line, and the slope can be the slope of the regression line. So here plot I plot the scatter plot and the regression line for the top density as the dependable variable, and the phase density is the dependent variable. And then this is the histogram of bootstrap beta 0 and beta 1. In the question 4, we need to compute the mean and the standard of the mean by using jackknife and equality histogram. So in this question, I set out a jackknife function as well. In the jackknife theorem, we need to remove each of the data once and save the rest as the sample. So here I set out a for loop, and the B is the remove the I data and save the corresponding data to the A and return A, and for loop for the length of x times. So the jackknife result can be a set of columns with the length of the fish density. So here I can use the jackknife function to sample the data, and then calculate the mean of each column, and the mean of each of columns result, and then print the result. And then the standard error part, we can is using the standard error function that we build it again, and with the JK parameter is true. And then we can print the histogram of jackknife mean of then fish density and the copper bar density. And the question 5 is we need to compute the regression coefficients and the jackknife standard error beta 0 and beta 1 with an applied histogram. In this question, we can do the same in the question 3 that we sample data with pairs. But in this question, we need to sample data in the jackknife way. So I set up a for loop and use the index negative I to remove each of the data, remove each of the index ones, and save the corresponding data to JK fish and the JK cop, and then using the regression B function to calculate the regression coefficient easily. And then just mean the BJK and the BJK1 is the first one is the beta 0 and the next one is the beta 1. And the standard error part is using the same way as well with the JK parameters true. And this is the histogram of jackknife beta 0 and the beta 1. And we move to the question 6. In this question, we need to compare the estimate for question 1 and question 2 obtained from normal theory, bootstrap, and the jackknife. To compare this result, I set a table to check whether there's something different between them. So, as we can see in the table, we can find that the mean and the standard error mean of normal theory and the jackknife, the results are totally the same, but the bootstrap are slightly different. I think it's the randomness of bootstrap when you sample the data, so it causes the result of the mean and the standard be a little bit different. So, okay, this is my presentation. Thank everybody.
Great. Very good. Questions or comments or any thoughts if you don't follow? Yes. You guys get the same result? More or less bootstrap. Because bootstrap random, everybody gets slightly different result, but for a normal theory and the jackknife should be the same. Okay? Or no one did homework instead of speaker? Anyway, okay, very good, thank you.
Thanks.
Okay, let's see the next one. This could be the question. Let's go ahead. Oops. Next slide. Does not work. Okay, let's do this way. Okay, go ahead.
So I started reading the Excel file into R, and because I didn't know we could use the RUnit function, so I just recycled the number generated from previous class that generated a number between 0 and 1. And then I multiplied that random number between 0 and 1 and multiplied the number of observation and use that as an index. So this bootstrap resample function gives me an new data frame of resample data with each column is a resampling event, and each row is the resample, the subsample I take using the index.
So how to um un, undo the auto. How you generate is not clear to me. How do you generate the random sequence?
Okay. So the random sequence was from the random number generator from the previous homework. So this gives me a number between 0 and 1.
Okay.
And then I multiplied that by the number of observations, and then take the ceiling, so that gives me a whole number between 1 and 34.
Okay, that's good.
So the resample gives me a table like that on the right, with each row is a resample, and each column is a sampling event. And then I calculated the column mean, and because the formula for standard error of the bootstrap is the same as standard deviation, so I just take the column mean and take the standard deviation of that. And these are the values I got. The histogram on the right are the bootstrap mean, and the red line is the mean of the original data set, which is the histogram centered around the original mean. So question 2 is to calculate the bootstrap median. So it's the same calculation as the question 1, but I changed the main function to median. And these are the values I got. Again, the bootstrap median is close to the center around the original median. And question 3 is to calculate the beta estimates from bootstrap. I made 2 new data frames. The first 2 matrices, the dependent variable data frame has all the fish density, and the independent variable has all the copepod density, and the second column, which are just ones, and that's called intercept. And then following the matrix of multiplication, these are the values I got for data estimates. And then for jackknife, I take the original set of observation, which has 34 numbers, and then repeat them 34 times in columns, and then remove the diagonal, so this creates a data frame like this. All the numbers are the same except the diagonal is missing. And then feed this data frame into the jackknife standard formula. And the numbers I got are these. Again, the mean I think it's not quite as good as Bootstrap, but it's still close to the original mean of the sample. And then for a jackknife estimate of betas, I have a for loop that removes one row from the original data at the time and calculate its beta 0 and beta 1, and so you set it in beta sample, resample 2. So this new calculation from jackknife, instead of 34 observation, it only has 33 at a time. And these are the numbers I got. I'm not sure why it's so far apart from the original mean, but it still calculates the standard error from the jackknife resample. And so I compare the value of normal theory, bootstrap, and jackknife. The normal theory and the jackknife have the same estimate of standard error, but the bootstrap is a little bit different, so instead of 61, it's 60 here. And the estimate of y-intercept, the standard error estimate of y-intercept and beta 1 are a little bit different between bootstrap and jackknife.
Okay, give more or less the same. So those are the different way of calculation. Questions or comments? Any parts you don't follow? Okay, very good. Thank you.
So the question also asks for the mean of the bootstrap resample and the mean of the jackknife resample. I didn't do that far.
I don't remember exactly that was a question, but you can check.
Oh, okay. Because I only calculated this.
I'm sure you do. I'm sure you did correctly.
Okay.
Yeah. So you just need to check my question and answer the question.
Okay, thank you.
That leave that. Okay. Very good homework presentation this week, and two nice features I like to talk about. So the first feature, build a function, right? So if you build a function, then you can repeatedly use that your own function. So that's a good way of running the program. And then the second speaker, actually, his homework one, he did a very efficient way. He didn't use loop. He used indexing and replicate. And actually, as I said in the very beginning of my lecture, you can take advantage of this matrix operation or indexing, and this will make the computation very fast. So actually, you can generate a bootstrap column 1,000 bootstrap index at once, and apply that 1,000 bootstrap index in the replicate of the 1,000 column of data, and then take a mean for everything altogether. So everything can be done super efficient without any loop. Median is the same. Okay, and also you create a replicate data and then remove a diagonal that create a jackknife sample set. That's also the most efficient way to create jackknife sample set instead of looping and remove one. Either way will be okay. Yeah, but if you do that matrix way operation, then the computation save a lot of time. And then actually, it's even for the second homework, you can do everything in a linear algebra. It's okay if you try loop. It's fine. But if you try to figure out the matrix dimension and calculation, in fact, all the regression analysis can be done at a single line and calculate the 1,000 beta 0, beta 1 at one line. Okay, if you figure out a linear algebra, so that's some part you can think about in the future without using flip. So everything again. The presentation for today are very good, and you realize that jackknife and the normal theory, assuming normal distribution, and the result are basically the same for mean and standard error for mean. But certainly for median and also for the regression coefficient, that's slightly different. And also, if you plot histogram, you realize that the bootstrap has more efficiency, right? Because they created many 1,000 bootstrap, 10,000 bootstrap, and the bootstrap output looks like almost Gaussian distribution, and that's a nice feature that actually we're going to need that feature for today in order to get a complex interval. Okay, it's okay. All right.
Yeah. Okay. A little bit comment on the second speaker. So next time, please make that your code visible, right? It's almost impossible to read in the back if the font is too small, right? So, you can please retype. It's like so people can really read your code because someone really want to learn in the way. For future speakers, also please make your code visible on the PPT, okay? All right. We learned how to calculate bootstrap standard error. That's mostly the important things. But jackknife is also important. A way of today we'll talk about that we are going to use the jackknife as a way to do bias correction. Okay. From previous homework we now understand how to get the standard error of something, which is very useful for statistics. All right. And then we all learned from the undergraduate if the data follow Gaussian, then we can take a standard error mean and then plus minus 1.96 standard error mean is a confidence interval, 95% confidence interval, right? So that's what we learned. But then can we really apply that concept in bootstrap theory, or can we do better, right? So today I'm going to say that we can do better. So I have this is the simple paper I asked you to read last week, and then I also recommend to read it. It's a very old paper, but this is not really anything to do with bootstrap, but this is idea about confidence interval for t-test. Okay, this is a very old paper, but certainly nowadays in our textbook we all fully understand how to get the t-test for that two sample t-test for me, but this paper is from the feature of the theory behind that two sample t-test. This is very old paper by Nancy Lowe, so she's Taiwanese. And then she worked in the United States in the fisheries agency for her entire life, and then she already retired. Okay. All right. So if we consider the same problem of estimating sampling error in theta hat, so in addition to that the standard error, you would like to estimate the 95% confidence interval, right? So the simple parametric approach is that you can, because you already have a standard error of theta hat using bootstrap, then the easiest way, simple-minded way is to calculate the bootstrap standard error and calculate 95% confidence interval like that. It's already said. But this requires assumption that all your theta hat generated a B number of bootstrap, right? 1,000 bootstrap. You have to assume that your theta hat is normally distributed. In your homework, you realize you look at the histogram. Oh yeah, this is not too bad, right? It's more or less like a normal Gaussian distribution that you can just use this very simple way to do the standard error, 95% confidence interval. So then you're done, right? However, if there's a certain, if in some other cases, what if the theta estimate does not really look like a perfect normal distribution, then we need a better solution. Okay. The easiest, so we call it non-parametric bootstrap confidence interval because we don't have to require the assumption that the histogram of your bootstrap theta follow Gaussian distribution. So I just made up some kind of histogram of your theta hat, and I call it theta hat I because they have B numbers of the theta hat, right? And then the easiest way is that we can then decide 95% confidence interval is 2.5%, and the other way is 2.5%. How do we do that? Oops. Okay. So the easiest way is that we have a theta I, right? We have theta I, and then we can rank our theta I from smallest to the largest. Okay, and then we can generate empirical CDF of all your theta I, right? It's okay. You just basically you just have to rank from the smallest to the largest, and then make it as a CDF, so some cumulative distribution function. Okay, so the smallest, the number 1 is this value, and the number 600 is this value, number 1000 is this value, right? You can do that very easy. You just have to rank them from smallest to largest in the location. And then if you standardize that 1000 into 1, that becomes percentile, right? It's percentile. Okay? And what is that? So you can rescale and then you create this empirical CDF, or we call it G function. We call it G function. Alright? So this G function is you transform from this to this. This code is just a convert your original data into the empirical CDF. Right? And the inverse of G is defined as the confidence interval, because as you can see, we can look at the location. So 0.025 here, 0.025 here, and they come down, and then this you get inverse, then you get theta I. Right? And the upper bound here 97.5 percentile, right? Then you get your theta I as the upper limit. Very easy. I just have to rank it. In terms of computation, it's very easy. You generate 1000 bootstrap theta I, right? Remember, one of them has to be your original data. One of them has to be original data, and you just rank them, right? So for example, you have a 1000 theta hat. What is the lower bound? Well, lower bound is 25th, right? Is your lower bound, and 2 point. If a 1000 number and the 25th location is your lower bound, and 75th location is your upper bound, right? Very intuitive. So because that covers 95% confidence interval. So that's the easiest way, simple-minded way to generate your 95% confidence interval using percentile. So it's called percentile, non-parametric percentile confidence interval from the bootstraps. Everybody with me for that? Very easy. Even the code is very easy to do, right? From your homework last week to the homework this week. So percentile CI is very easy. You just need to rank them and find the location, right? Okay, any question for that? That concept is very important. The important concept is that we are able to convert your vertical. The idea is that no matter what, if you generate your theta I, we are able to generate a CDF for your theta I just by ranking them. We can always do that because it always rank them, right, from small to largest. Even if you repeat it, it's okay. We can always rank them. And then so we can always create a CDF, empirical CDF for your theta I. And then we can get something outside the CDF theta I. So there's a one-to-one mapping, always one-to-one mapping between your percentile and then your theta I. And if you get a theta I, if you are interested in any theta I, you get inverse, you get a percentile, right? You can know from this function you can get from here to here, you get here from here to here, right? Because there's always one-to-one mapping, only one-to-one, right? Almost, because there's some number can repeat it, so slightly, not exactly one-to-one, but theoretically, it's always one-to-one. Okay, all right. So in this case, we do not require that cumulative empirical CDF follow Gaussian distribution, because in this case we do not need any assumption. the data does not need to follow Gaussian distribution. We can still always get some kind of percentile location, right? So without any assumption. So that's the easiest way to get percentile. However, so I would just say that just A that because we need a median number, just to remind you that this is a very simple high school concept. Is that n is a number of bootstraps, okay? And then you of course median one, and if the n is even, the median is the mean of these two numbers, okay? So you can sort the data in the nth percentile, right? And then you get a percentile combination. So in practice, I already explained it's really easy. All right. However, the experience has shown that these simple bootstrap percentile combinations are frequently biased. Okay, and then we will introduce two ways of make a bias correction. One is the simple way called BC method bias correction, and another one is called BCA bias correction with acceleration. I'll explain what I mean by acceleration. And the bias correction is needed if G theta hat is not equal to 0.5. Here, theta hat is the theta hat calculated from your real data. Okay, calculated from your real data. If the real data is not exactly in the median, then you need a bias correction. Okay. Why? Suppose this is I'm going to draw something on the board, okay? Can you see the board, okay? In a perfect case, again, this is already standardized CDF. Suppose, try to draw here. Sorry that it's difficult to draw perfectly. Suppose you observed theta hat. This is from your observed data. Is exactly the median. Is exactly in the middle. Then of course that 95% confidence interval generated from percentile method is reasonable, right? Because the coverage in such a case, the coverage in terms of probability, you can imagine the coverage here. I'm going to draw the line here. The coverage here, in terms of probability coverage, confidence coverage, like symmetrical, right? If you choose 95%, this direction, these are exactly the same. The coverage is perfect, symmetrical. Okay, so if this median, if that observed, I call it OBS observed, is exactly median, then we don't have to worry, right? Because the coverage is exactly perfect. Okay. Suppose in a very terrible situation, here, a terrible situation, right? You observed, theta observed, like that. It's not at the median, it's at the 0.4, like 40 percentile. at 40 percentile. Then if we use simple-minded percentile confidence interval, we're going to have that. This is the same. We normally we choose that and choose that. Right? If you do that, then you are not wise, because in such a case, the coverage here, very different. Very different. Right? So this is the upper bound is too far away from your observed theta, and the lower bound is too close. So the probability, in terms of probability, now I showed this a distance, but you have to imagine this is, we have to consider in terms of probability. This does not follow the exact understanding of a confidence interval. But confidence interval would have a equal probability coverage on both sides. Right? So that's how we define the confidence interval. Right? So if you use in this case, if you use a percentile approach, then you made a serious mistake, because under this condition, that coverage is not fair on both sides. Right? So if this happened in your real world data, you need some slightly change in so-called bias correction in order to make your coverage both sides have an equal probability. Okay, not equal distance, that remains equal probability. And how to make that? How to make that? So we have to be back and forth. So this the classroom is not best one. I always ask some other classroom, but I cannot get it. Classroom is difficult to explain. Okay, so to explain the bias correction, let's review the concept of the Gaussian CDF. Okay, so that's a very simple Gaussian CDF I created. All right, and then if in the standard unit Gaussian distribution, the mean is 0, right? And the variance is 1. Okay? So that's a CDF of your unit Gaussian, right? And then again, that's a cumulative, so from 0 to 1. And what is the median? The middle, in terms of basically the median would be 0, right? By definition, mean would be the median to be in the middle of that order distribution. Like everybody understands that. So this is common sense to everyone. Suppose X follow the CDF, normal distribution, unit normal distribution, standard unit normal distribution. Then the minus 1.96 is your lower bound, okay, 0.025, right? 0.025 here, right? So, and the 90% coverage, 0.05 or minus 1.64, and the 0 is 0.5, and the plus 1.96 is 0.975. Right? Everybody understand this, right? Because that's the normal, that's how we get the 95% confidence interval in our undergraduate textbook, right? So everybody understand that. And the Gaussian CDF, that's the formula, and then we are always be able to get inverse, right? Get inverse. So again, this is the CDF from unit Gaussian. When I say unit, that's unit. Okay, that's unit, standard unit Gaussian. So we are always able to map 1-to-1. If we get this, we can map this one. If we get here, we can map come up with this, right? And then we also in the textbook we know this is called z-score, right? This is called z-score. How can you get z-score? You just have to take your data minus x bar divided by your standard deviation. You get z-score, right? That's the undergraduate dependent. So you are always you always so because there's simple one-to-one mapping. If you get this, you can get this score. You get this score, you get your 5, right? You get your 5. Now the idea is that now we are going to use this concept, but I'm going to generate the empirical CDF, as I already showed you. And the empirical CDF, it has this normal CDF, always have one-to-one mapping, right? It's okay? We talked about the probability theory slightly a little bit in my first lecture, right? Because all the CDF is accumulated from 0 to 1. So all the CDF, no matter what's underlying PDF, always is a one-to-one mapping. That's a fundamental law of probability. All the CDF has a one-to-one mapping to other CDF. Okay, always one-to-one. Okay, because the CDF is a monotonical increasing function. There's always a one-to-one mapping. Okay. Okay, now, of course, we need to calculate Z0 hat from your theta hat, right? Because we say if the theta hat is at the median, then we don't need a bias correction. If theta hat, for example, if G theta at the median, which means the G theta hat, sorry again. So if theta hat is the median, then G theta hat is actually 0.5, right? What happens if G theta hat is 0.5? If G theta hat is 0.5, then Z0 equal to 0, right? It's okay? That's from the Gaussian CDF. It's always true. It's always true, right? It's okay? Question for that? This is very critical, otherwise it gets really confused. So, which means if you generate an empirical CDF of your theta hat, then you find the observed, I call it theta hat as an observed theta. Okay, theta hat is observed theta. Okay, so from your original data. If that theta hat is exactly at median value, then you don't need a bias correction. Which also means if you make the z-score of your theta hat, right? If you calculate the z-score of your theta hat, now everybody understand how to calculate the z-score of theta hat, right? Right? If you calculate your z-score of your theta hat and find the z-score, I call it z0, is 0, then we don't need a bias correction because it's exactly in that perfect position. Right? You can just use a percentile approach. However, if you do that calculation, then you find G theta hat is not 0.5. Okay, not 0.5, which is not in the median location. Then, of course, Z0 is not 0. Right? Z0 is something different from 0. Maybe plus, maybe minus, depending on where the location you are. That's theta hat among the people CDF. Right? Okay. In such a case, you need a bias correction. A formula, let me explain the formula first, because that's a very important thing for you to do your homework. And then I explain the theory behind the formula. Right? So the formula to do the bias correction, so I call it bias corrected alpha divided by 2. What is alpha? Alpha basically, you can define 0.05, right? In a typical case. Of course, you can define 0.1 or other number if you wish, but the formula is the same. In the example, I'm going to just use alpha as a 0.05. So this is lower bound and this is upper bound. And then the formula to calculate your bias correction, the lower bound and upper bound is this formula. Okay, this formula. So Z0 is that from your observation, right? From your observation. And what is Z? Alpha divided by 2. If alpha is 0.05, everybody understands is plus minus 1.96. If you follow Gaussian distribution. Okay? And the reason we are going to take advantage of the Gaussian distribution because we should be always map 1-to-1 from your empirical CDF to a normal CDF. There's always a 1-to-1 mapping, right? And then because we fully understand the probability theory of the CDF, normal CDF in terms of 95% confidence interval, so I'm going to map a lot and make a bias correction and map back. Okay, so that's what we're going to do. Okay, so basically we need to shift some kind of location because location is not zero. This zero is not zero. We have to shift your location. Okay, and then create a bias correction and in the space of Gaussian and then map it back. Okay, and we can always do that because there's always a 1-to-1 mapping. So this is called a transform in probability. Okay, transform in probability. Okay, and in this way we are able to get the correct coverage in the correct probability because the correct probability always can be derived from the Gaussian CDF. Right? So in terms of computation, it's a very easy. For example, first, you get your data, you get your theta head. You find your location of your theta head. All right, it's 0.46. It's not 0.5. You need a bias correction. And you need what's your bias correction formula? This one, right? Z0. If you plug this in to your, if you plug 0.46 into your Gaussian inverse CDF, you find out Z0 is minus 0.1. Right? You get your Z0. You can always get your Z0, right? Then you just have to sort it. You just have to sort all of your theta I and find the location of your theta head. You get this, and then plug in, you get your Z0. Like get your Z0 out. You can use the built-in function or inverse CDF in your homework. You can use your inverse CDF because we need to get inverse back in and back forward, backward. So you can use the built-in function to save your time to get your inverse of your normal CDF. Okay. And then if you plug this number in, right, then you get your 95% confidence interval. This number, and then you get an inverse. So when you get an inverse, you get some kind of location, like 0.15 here, 0.96 here, and then you, from your empirical CDF, you find out the location, your location. Okay, that's how you get your bias corrected confidence interval. Any question? If you don't understand, I'll explain again. Okay, let me explain again. I have not explained the formula. Okay, I have not explained the formula. I have not explained the CA required bias correction like that. I will do that next. But given that formula, do you understand how to do the calculation? Okay, so let me explain how you do the calculation. Is first, you need to decide your Z0. Right? You need to decide your Z0. You need to rank all your theta I from small to largest, and you find the location of your theta head. Right? And it has, in this case, is 0.46. It's not 0.5. So you need to do the bias correction. And what is Z0 of 0.46? Right here. Right? So 0.46 is here. You can get your Z0. So, right. You can use the function. You can use the R function of inverse normal CDF. You can always do that. But what it really do is that looking at this figure, and then one. Of course, not exactly doing that, but you can imagine that's how that code is doing. Right? So it's looking for that, give you Z0. Okay, so you get a Z0. Okay? And then you plug in this formula, right? You need to get a G inverse of something, right? That something is this formula. Right? So you just add z0 here or here. Right? So you get your lower bound and upper bound. Right? Lower bound and upper bound. This z corrected z corrected upper bound, lower bound. But that correction is in the Gaussian space. That correction is in the Gaussian space, not in your empirical space, right? So after you find your upper bound here, lower bound here, is no longer plus minus 1.96, right? It should be this number and this number, following this formula, right? Now I have here and here. I have here and here. I'm going to project to get your G function. Project to get your theta actually here and here. 0.15 and 0.96. And because there's a one-to-one mapping, you can then now map here. Right? And then you go down because this is just a rank of your data and then you can find your location. Alright? Is it okay? Oh, is it okay? If you don't follow, I will explain again. So basically, this is an operation in the Gaussian space. They find a location, and because there's a one-to-one mapping from your empirical CDF and normal CDF, the location is a one-to-one mapping. And you decide location, you find a real value. This is the percentile. And then you get your empirical G minus, G inverse, and then go this way. Go this way, get your real confidence interval, lower bound and upper bound of your theta hit. OK？ 懂吗？需要再解释一次吗 ？OK？ This is really fundamental concept. Is it okay? All right. All right, then I explain. This is maybe not so critical for most of people because you know how to do the calculation. That's okay, right? And then, but then I'll explain why. I'll explain why we have this formula. Okay, why I have this formula. Okay. So this goes to the probability theory that the assumption that is made to construct bias corrected confidence interval for any theta is that this monotonic increasing transformation of estimated theta exists, such that the transformed value of f of theta hat are normally distributed with the mean shifting that certain location, and the standard error equal to 1. That sentence basically say what I already explained previously. Okay? All you really need to do is shift your location in the Gaussian space, right? Because if this is 0, then nothing has to be done, right? If this is non-zero, you have to shift some location of your mean value, right? But by definition, this is the definition of upper bound and lower bound. This is the definition of upper bound and lower bound. Right? If this is 0, in fact, this is 0, this is the mathematical definition of upper bound and lower bound. Okay? This is fundamental definition of upper bound and lower bound. Without looking at that. Okay? That's how we define confidence interval. Okay, this is how we define confidence interval. Alright, and now if we shift to some linear algebra, and I'm going to find the f of theta. So you have to do some algebra, it turns out like that. Okay? You just have to yeah, I have to move this side and then move this outside to that way also. So that's okay. And then you untransform this limit will give you confidence interval for theta. Okay, and then we can always find z0 as described previously. Okay. All right. Follow up. So I'll give you an example how to get to your upper limit. So this is now your upper limit. So I let PU is upper limit. Probability upper limit be the probability of being less than this upper limit for bootstrap distribution. Okay, we need to find the PU. So what is PU? PU is a probability that's smaller than that one. Right? So this is this. Okay. So this is just some linear algebra. I move this to this side. I do some algebra. I create this. And what is this? This is exactly the unit. There's a map to the unit Gaussian z. Okay, z. If you do this, then z is a standard normal distribution. So that's how you come up with this formula. All right, and for the lower bound, you can do likewise. You get lower bound. Okay, so up to now, I explained the approach of BC. Okay, I explained the approach of BC. So the BC adjusts the critical percentile. Okay, bias correction they just adjust the critical percentile to estimate the confidence interval. If GC hat is not exactly the median, then that is the formula. Okay, that is the formula. I try to have a minima mathematics to explain how we come up with this formula. It's okay. And then I realized in the past that there always someone has trouble understanding that transform in probability, right? And how that formula is calculated. Then it's not so easy for me to explain that all the details because you need to understand the mathematics, statistics, the probability theory to understand why by definition it should be like that, right? So I'm not able to give a limited amount of time, and I find that trying to explain that does not help, all right? So if you understand, that's perfect, right? If you don't understand, you can try to understand. If you don't feel like to understand the mathematics, the bottom line is that you understand the formula, okay? You understand the formula, and then so this is the formula, right? And this is the example how you do the calculation. You just need to write a code to do the calculation likewise. Okay, that's a minimal requirement for this homework. Right? As long as you know how to do that, then even you don't understand why this is the formula like that, it's totally fine. Okay, maybe at this moment. If you in order to have a better understanding of that, you have to take some class about probability and also some mathematical statistics theory to have a better understanding. What's the definition of confidence interval? Right? Definition of confidence interval is not that this is like confidence. This is not the mathematical definition of confidence interval. Okay. The confidence interval definition should be like that. It's okay in terms of computation. I hope that you are fine with that. Okay, before taking a break here, I'm going to talk about the bias correction with acceleration. All right. So the BC and the percentile approach assume the standard error of theta hat is a constant. Okay. However, in reality, standard error of theta hat is a function of theta. If we have a bias. If you have a bias. Okay, so the bias correction have to correct for that. or not. Actually, that standard error is a function of theta. The correction is made by calculating the coefficient A. A is acceleration coefficient. Acceleration, how do you calculate it? Actually, it is the dSE d theta. Okay, dSE d theta. All right. Of course, you ask, how do you do that? How do you do that? Okay. So I will explain the next. I will show the formula, but I will not explain the mathematics how you do that. Right. So the bias corrected with acceleration confidence interval following this formula. So this is the formula you have to understand. Okay. So that's basically you need to calculate acceleration coefficient A. Then you plug in this, and then everything else will be repeatedly as the previous one, as BC. So keep in mind, if A is zero, right? If A is zero, this is 1, this becomes bias correct BC, become BC. Automatically become BC, right? And if Z0 is 0, and automatically no bias correction, just percentile. Okay? Okay, so the question is how can we estimate A? There are various ways to estimate A, but the easiest, the more or less good approximation is to estimate A using jackknife estimator. Okay, and A is following this formula. What is this theta dot? This is mean of your all jackknife theta. Okay, and theta I is your jackknife theta I, right? And following this formula, you can estimate your A, parameter A. Okay, this is given without mathematical explanation. Okay, I decided not to explain this. It's just not very useful for students here. So you just have to follow that formula. Okay, how is it generated is related to the jackknife bias correction that we talked about in the previous week. And then we have a Taylor expansion, and then you do some calibration, and then it ends up with this formula. Okay, and that is not very useful to explain that. Right? Okay, in the past, I realized not so useful. So even you don't understand why we come up with this A, you can always calculate. So that's bottom line. You can calculate A, right? Because you know how to generate your jackknife and jackknife symbol and jackknife mean, and then you plug in and you get A. Okay? And if you get A, when you get A, you need to plug in A here, right? Because everything here are available. Z0 is from your theta hat, right? And this, what is this? This is depending on alpha. If alpha is 0.05, that's which is plus, that which is 1.96, right? 1.96. So actually you have all the formula, and then you take advantage of your Gaussian CDF and inverse Gaussian CDF and project into your empirical CDF, that you can always get BCA. Okay, if you know how to do BC, you just plug in A and then you know how to get BCA, right? It's okay? All right, good. So this is just some example from that paper I asked you to read. Okay, again, that's the SAT versus GPA, and then you get a correlation, coefficient, and then you get a bootstrap histogram, and that's how you following that approach. In this case, they use alpha 0.1, right? If you choose alpha 0.05, that's fine. And this example, they choose alpha 0.1. Okay, but in any case, you are able to calculate the bias correction, the bootstrap, lower bound, upper bound. Okay, the BCA, lower bound, upper bound. And this is called standard bootstrap. Standard bootstrap is percentile approach, lower bound, upper bound. And this is the if you assume the data follow Gaussian distribution and have features hyperbolic tangent transform and you get back and forth and you get this, right? Okay. All right, I'll stop here, take a break. Before I take a break, any question? Okay, or you can ask during a break. We'll come back at 10:40. Okay, 10:40. give some example on different hypothesis tests and how we can use Bootstrap to deal with those statistics issues such as t-test and other things. Okay, that's just some quickly through some example, and then I'll talk about more complicated issue with the data structure and then different a better solution for the Bootstrap. Okay, this is the t-test, right? You have given data of two populations, right? You can calculate the theta hat, you calculate the standard error of theta hat, and so on. Okay, of course we can do that. But what can we say about the difference, right? Data, big data, is that theta 1 hat minus theta 2 hat. That is simple. So if it is bigger than 0 or smaller than 0, right? That's typical t-test. You learned from undergrad, typical t-test. All right, so this is a review t-test that I'm not going to talk about, right? This is, again, remind you, if you don't remember what is simple two-sample t-test, or what is the pair sample t-test, right? Something like that. If you don't remember, take it after the question. Test week. Okay, I'm not going to explain. Right? Okay, so now if I have two samples, right, and then I can then decide the upper bound and lower bound of that confidence interval of this sample, okay, and then again this is another sample, and then that's the lower bound of this sample, okay, and the simple-minded confidence interval test is to ask whether the upper bound of the first sample is smaller than the lower bound of second sample, right? So whether that the confidence interval overlap. You know, this is simple-minded, very strict, very conservative hypothesis test, right? Right, and then if you're interested, you can read this paper I put on the NTU Cool, okay? So we can imagine some kind of t distribution if the sample size is small, right? We can use as t adjustment. So we can then get the confidence interval of your CI, okay? And then of course, if you use Bootstrap, you can estimate your standard error of your X bar, right? Here you use the basic approach, and then you can assume the following t distribution. Okay, and then in all time, right, people statisticians discussed how do you decide that hypothesis test, right? The very strict, very conservative test is that the confidence limit don't overlap. I already give example, right? That is very strict, 非常严格, very conservative test, right? And then the less conservative test is that whether S1 bar is not included in the confidence interval of S2 bar, or S2 bar is not included in confidence interval of S1 bar. Okay, so this is more liberal, right? That's whether it's basically ask whether that mean is included here or not. Right, included. That's a different way. That's a different way. All right, and nowadays everybody agreed the best way is to calculate the difference of mean, right, in the confidence interval of a difference in mean, right? So that's why you learn in t-test, right? You calculate the difference in mean and confidence interval of difference in mean, right? And then whether that is to 0 or not, right? That's a t-test. That's a standard two-sample t-test. And then this is just some exercise she did that she tried the data generated from this different distribution and what's the best way, okay? And certainly, of course, you understand that as nowadays we understand the third method is best, right? Third method is best. We need to calculate the confidence interval of the difference in mean would be the best, right? And then whether S whether it's greater than 0 or not, or less than 0, right? So the question now is that how can you calculate the confidence interval of difference in mean, right? You can do this way, and then you get the standard error of difference in mean, okay? And this can be approximated by this approach, right? Certainly, if you learn t-test, right? So it's here. Is depending on whether you have a poor sample and so on and so forth, right? Actually, you get the poor the standard, you poor the standard deviation and use that as an approximation of your standard error of difference in mean, right? So that's t-test. All right, so this is just a quick review of the t-test and the history, some t-test, how you do that. All right. Okay, and then if you have a large sample size, of course, you can have this kind of, no longer, you don't require t distribution. The large sample size is just z distribution, right? Because the large sample size, t distribution approximates z distribution. All right, so how happened with the bootstrap? Now, we are able to estimate the theta 1 head and theta 2 head, and also we can estimate theta standard error of theta 1 head and standard error of theta 2 head. Right? Of course, you can say, now I'm going to just use this formula to estimate the standard error of your difference in mean. That's possible. But during the process, in fact, you generated many theta 1 head I and theta 1, theta 2 head I, right? You generate a lot of samples. And then you can calculate, you can generate a lot of the difference in mean. Data 1 star, data 2 star, data 3 star. So you generate many difference in mean. Right? You generate many difference in mean. Okay? And because you have many difference in mean, and you should be able to generate the lower bound and upper bound of your difference in mean. Right? Instead of generate a confidence interval of your theta 1 head over theta 2 head, what we are doing now is generate the confidence interval of difference in mean. Right? Difference in mean. Is it okay? Yes or no? Okay? You can given first sample, you can generate theta 1 head, right? Given the second sample, you can generate theta 2 head. And difference is the difference in mean from your bootstrap. So you can do a lot, you can do 1,000 times, right? And then you ask whether or not, so you generate histogram of your data. You can do it many times, you can generate histogram of your data. This histogram does not need to follow Gaussian distribution. You're very lucky to follow Gaussian distribution. That is not an assumption required. You do not need that assumption. Because in any case, you are able to generate histogram of your data, right? And then you can have a BCA lower bound and upper bound, right? And you ask whether the 0 is included in the lower bound or upper bound. If 0 is included, then you say difference in mean is not significant, right? If this 0 is outside your lower bound, maybe this way, maybe that way, maybe here outside or here outside, anyway, that you say you reject null hypothesis, right? Because the confidence interval of your difference in mean does not include 0. Right? The philosophy is exactly the same as the t-test. However, here we are going to, instead of assuming t distribution, instead of assuming Gaussian distribution of data and t distribution over your statistics, we don't need any assumption. We just need to generate bootstrap difference in mean. Okay? And that's simple independently because there's no pair, right? If you make a pair, it will become pair t-test. Right? If you make an independent sample, bootstrap sample, then it's independent two sample t-test. Okay? Right. So you can do that, then you can understand whether you can evaluate whether your data, whether you reject your null hypothesis or not. Okay, and of course you need to worry about is the one sample, one tail, the two tail, then there's something you have to figure out. Okay, it's slightly different. This is part of the homework. I let you think about it. One tail, two tail. Okay. All right, there's another application used for application of bootstrap. For example, if you do the molecular phylogeny, you get the DNA data, and then you find some kind of similarity or some kind of common ancestor and so on and so forth, slightly complicated, but you can always make it as a phylogenetic tree, right? So it's evolutionary tree you learned from your evolution or ecology or biology textbook, right? And you read a paper, there's a lot of papers say, okay, this is a tree and there's some number. They say that the bootstrap number, okay? And then we know if you bootstrap 100 times, then 90 is good, 95 is good, which means that a lot of support from bootstrap. What does this number means? This number means basically is that they resample the bootstrap the data, and then generate the tree again, 1,000 times. Okay, in this case maybe 100 times, right? 100 times, and then that 95 means out of 100 times, there is 95 times the split is consistent with the real data. Okay, so which means that you only resample your data and then so that your bootstrap number. So in this number high means that split is more competent. Right? If it is low, which means this may not be competent. This lab claim is not resolved if you listen to some lecture. Right? So they have following the tree. So that's what you do if you do that. You just have to regenerate. You have to decide some kind of algorithm, make a tree, and you bootstrap, make tree, bootstrap, make tree, bootstrap, make tree. And then they count that numbers. Okay? So that's bootstrap number. I already say that. Okay, I talk about homework first, then I have more bootstrap to explain, some structured bootstrap. So homework, following the previous homework, right? Now we are making a regression. A lot of you already calculated beta 0, beta 1, right? And then in the previous homework, I asked you to calculate standard error of beta 0, beta 1. Right? Here, I only focus on beta 1 because beta 0 is intercept. Right? Where I ask, you are going to have a hypothesis test whether the regression is significant, right? Which is equivalent to whether beta 1 is 0 or not, right? If beta 1 is significant different from 0, then we reject no hypothesis, right? That's it. In a regression, instead of F test, we can have T test on the coefficient. Yeah? No? Yeah? No? Okay, in the regression analysis, there are two ways to evaluate whether the regression is significant. One way is F-test. F-test whether the regression line displays sufficient variance of your data. Okay, and last is the mathematical equivalent to ask whether the slope is significantly different from 0. Like two test results must have the same conclusion. Okay. So either way will work. You just need to do one. Here we choose the easiest one. We choose to test whether the slope beta 1 is significantly different from 0 or not. Right? How can you do that? I'm going to generate 1,000 bootstrap beta 1 and calculate confidence interval of your beta 1. Right? And ask whether that confidence interval includes 0 or not as a decision whether you reject your hypothesis. It's cool? Okay? Without any assumption of data. Okay? And then we introduced three methods. Simple-minded percentile method, right? BC, BCA. So you have to do that. Okay? You have to do that. So this is a regression bootstrap test of a regression. Okay? Very simple. Y and X. Very simple bootstrap regression hypothesis test. Question 2, again, very simple, is a bootstrap test whether significant difference exists between the density of two species. Okay, two species. Density, not proportion, okay, density. Alright, because in your first homework, you already calculate density for every species, right? That's part of your homework. First homework, EJ asks you to do the homework. You calculate density for every station, for every species. You make a matrix, right? So you take out you check these two vectors, right? So that's your data, and assuming that data as just random sample, okay, random sample, right? And now I have two sample t-tests. A test I will ask. So of course you can calculate the theta 1 head for this species and theta 2 head for this species, mean of this species and mean of that species. And you ask the difference in mean and whether the confidence interval of difference in mean equals 0 or not, right? Okay? And then of course you can try all different methods, but I ask you to only do BCA because BCA is the most complicated one. Right? If you know how to do BCA, you know how to do BC, you know how to do percentile, right? So this is BC. And then, of course, in that data set, there's a season, there's a spatial structure, right? So you cannot just simply do the independent t-test. But here, it is to simplify. I ask you to assume all the data are independent. Okay, all the data are just two columns of data. All right, don't worry about the space, the season, and this is irrelevant in this homework. Okay. So don't make it too complicated. Assume that all the data are independent, each data are independent. So you have two sample independent, two sample t-tests, and then independent, all the data are independent, and you have a simple regression test. Okay, that's your two homework. All right, and as a reminder again, for the regression, you have the sample with pair, right? Sample with pair. And for this one, the sample with pair or the sample without pair has a different meaning. You can try. Okay, you can try. If the sample independently without pair, that's in two sample independent t-tests, right? If you sample with pair in this question, you get paired t-test. Everybody understand paired t-test and the two sample independent are completely different concept. So you can try. Okay, you can try either. You can try both. You can try both. Again, because the previous homework, you already know how to make bootstrap, right? Generate bootstrap sample, and you just have to write a code to get the confidence interval, right? So, and again, and as such, you don't really need a built-in function. Of course, you need a built-in function to get in order to get the normal PDF, inverse, and so on and so forth, CDF, you can use this built-in function, okay, to get the projection. Get a mapping from the G map to phi and so on and so back and forth, because that's you need that to get the location. You can use that. You can use that built-in function. That's your homework. Okay. Before I continue, volunteer for homework presentation. Okay, already two gentlemen in the back. All right. Okay, I assume there's no question on homework. Then I will explain a bit more on efficiency of bootstrap and how can you make that bootstrap more efficient, and also how can you deal with the issue that when you have a spatial structure in your data. Okay, so more on bootstrap. This is a review already. I know you know this already. I skipped this one, and this already explained. All right. Regression. In your homework, I asked you to do a very simple regression. This week also a very simple regression. But in real world application, the bootstrap regression can be, the efficiency of bootstrap regression can be improved using this approach. Instead of, in the homework, I ask you to bootstrap your sample in pair, right? You bootstrap X and Y. Okay? But the bootstrap in X and Y has a problem is that you always, because this sample is pair, right? They have a limited number of combinations you can choose. Okay? And also, if you have some value is extreme, that value is very influential. Right? Value is very influential. For example, you see the board? So suppose we have a data like that. So this one is very influential, right? Maybe make me this too bad. So you may make a regression, and this one is very influential. Right? So this is not too bad. Still looks like a, line by line. However, if we have some point here, then it's tilt substantially. So this one is very influential. And if you do the bootstrap, sample the data with pair, there's a certain chance you get this one. But if once you get this one, you get tilt. If you don't get this one, you get everybody don't have here. So you have two models. Maybe you create some kind of very strange distribution, empirical distribution of your beta one. Right? And then if you don't care, then of course you get, well, that's the reality, you get confidence interval over your beta one. Okay. However, that confidence interval is not reliable, right? Okay. And also, if you do that, there's a limited number of bootstrap you can choose. Always limited. If the data, 20 data points or 30 data points, the potential bootstrap sample is limited. And then your histogram is not smooth. Okay. So to improve the efficiency, another way to do the bootstrap is instead of bootstrap the original same data, instead of bootstrap from original data, we bootstrap epsilon. Bootstrap residual. So this is called a residual bootstrap for regression. Okay, residual bootstrap for regression. So, of course, everybody understand this now. If you learn undergraduate statistics, right, you get you can calculate the best fit of your beta, right? Best fit of B. You get best fit of beta 0, beta 1, right? And then of course you get given this line, right? So here, maybe not too big with it. Okay, about this one for now. Let's say this. What's this? This is epsilon I, right? These are residual, right? So it's called a residual, 残差, right? Residual after your regression. So what is this line? This line is a y equal to bx, right? So after you calculate that, so your yi hat is bxi, right? So this is prediction, this is this point. So this is yi hat, right? So this is your regression. And what is yi? Yi is bxi plus epsilon I, right? 对吧? Is it okay? So this is a review of your regression. And we are always able to do that. Right? We are always able to do that. So right now, the important things is here. Important things here for the bootstrap is your epsilon I. Now I'm going to bootstrap epsilon I. So ideally, how can you bootstrap epsilon I? If you choose randomly xi, of course, you find your yi hat, right? Because that's the regression line, you already for sure you choose. It's no longer in the data. You don't have to choose from your data. If you like, you can choose here. Basically, you choose it from our data usually. So I'm going to choose this one. Right? Go choose this one as your my si, and then of course I get the my yi here. But if I choose this way, everybody eventually align on this line, right? Then there's no uncertainty. There's make no sense, right? But there's uncertainty. There's uncertainty. Where is the uncertainty? How do you incorporate uncertainty? This is your uncertainty, right? This is your uncertainty. I can then plus something. I can plus my epsilon. In fact, I have many epsilon. I have many epsilon I. I have many epsilon I. So when I decide xi, I already decided yi hat. And I randomly plus some other epsilon I. There may be some way, maybe this one, maybe this one, maybe this one. Doesn't matter. They can choose with replacement. Because I have a column of epsilon I can choose randomly. I can bootstrap. I can choose randomly. So when I bootstrap residual, ideally, I can randomly choose a SI. I automatically generate YI according to regression line, and I plus some random residual. And that random residual is sample, bootstrap sample from the column of your epsilon I. Okay? The idea is okay? Okay? Any question for that idea? Right. Good. So instead of bootstrap your data in pair, I'm going to just bootstrap X, and then I'm just randomly choose X, and then bootstrap epsilon I, and then create a much more different combination. So that's the bootstrap residual, the basic idea of bootstrap for regression. But we can do even better. Okay, now I'm going to explain. So that comes back to that linear algebra of a regression model. Now I already explained how we calculate B, right? Everybody know how to do that. And what is y hat? I talk about y hat I. How can you get y hat I? You just do the linear algebra, you x multiplied with b, get your y hat I, right? 就是把那 coefficient 乘上去嘛，对， you get your y hat. For every, but I write it in the matrix way, right? So x is a vector, is a matrix, or a vector of data, depending on your one variable, two variables. So x can be a matrix. If you have multivariable x, y, and so on, you have a matrix of your x. But x multiplied with b, get your y hat by definition of linear algebra. Okay. So what is b? B is this. I just write B is here. Okay? And then I can write this as hat. This is called hat matrix. Why is it called hat matrix? This is because if the original data vector of y multiplied with h, get y hat. So this is called a hat matrix because that matrix is used to transform yi into yi hat. Okay, so it's conventionally called a hat matrix. Okay? So then hat matrix H is an n by n matrix called hat matrix. By definition, it has to be n by n, okay, squared. Function. And what is the epsilon? Epsilon, of course, y minus y hat is by definition your epsilon, right? Right? Y minus y hat is the epsilon. Okay. So given the hat matrix, you are able to get epsilon. Okay. So what is epsilon? Epsilon in linear algebra form is I is identity matrix. Okay. I is identity matrix. E 啊，整排都是 E， diagonal 是 1. So y. Okay. So the difference between y and y hat is by definition your epsilon. And I write it in matrix form. And hat is a square matrix, okay, n by n square matrix. And hi is a diagonal entry of a hat matrix. Okay, it's called a leverage. By definition, hi between 0 and 1. Okay. What is the meaning of hi? Hi is called a leverage. Okay, 杠杆. Hi is called a leverage. Leverage is a mathematical definition in terms of regression is that the extent to which the fitted y value was influenced by the actual y value measured at the x value. Okay, what does this mean? In your regression, in your regression, some data are more influential than other data, right? Remember, that's your data spanning, right? The data here, and data here, data here are more influential, right? Compared to data in the mean, in the X bar, Y bar. Right? Data here are less influential. Data in 2n are more influential. Right? And also, if the data like that, you have the data like that, also influential, right? Because it deviated from the tendency. This one also very influential. Okay, there are two ways you can influence your regression. One is really that point align the regression line. Second is that how far that data point deviated from your mean S bar, Y bar, right? So we learned that from your undergraduate statistics. Right, so we also remember we can calculate the confidence interval for every predicted number, right? And that confidence interval like that, right? Okay. So in fact, every data point contributed to the regression line, but the contribution of a different data points differ depending on the location, depending on how much they deviate from that regression line. Okay? And that is HI. Okay, HI is a quantification how much that data influence the decision of your regression line. Okay? This is not a very perfect mathematical definition, but conceptually. It's okay? And then because we want to bootstrap your epsilon I, right? But if some epsilon I is more influential than others, it makes no sense. Right? Because now we have to follow, we want to bootstrap your C epsilon I, and that epsilon, an idea that epsilon I would have an almost equal contribution. Okay? Then that regression line has a better bounded confidence interval. Okay? So we need to standardize our epsilon I in a way that all the epsilon I after standardization, all the epsilon I have equal leverage. Otherwise, some epsilon I is going to be more influential than others. Then the problem comes back again. This is very influential, and then that tilt a lot. Okay. So that's a more conserved confidence interval calculation. Okay, you have to adjust your epsilon I. Now, because the leverage over the contribution over your epsilon I can be calculated from your I hat, then you can then make adjustment. Right? So this is so RJ is called modified residual. RJ is called modified residual, or some people call it standardized residual. Okay, how you standardize that? This is already this is epsilon I, right? The difference between y and y hat. That's epsilon I, and you divide it by this. And then of course you want the y divided by this because by definition the variance of your each residual follow this formula. The covariance matrix of your residual actually follow this formula. Okay, and then this is the variance of your data, the variance of your residual, but adjusted for that leverage. Okay. If that concept very difficult for you, the bottom line, if you this, you don't have to do this for homework, but this is in your real world application in your research This is a better way to do the regression. Okay, a better way to have a is a better way to construct confidence interval of your regression. Remember is that you have to calculate modified residual following this format for harmonic formula. Okay, and what is Hj? Hj can be obtained by this. Okay, and the diagonal entry is your Hj. Again, in terms of computation, this is not so difficult. Okay, so if the concept is difficult, but I think the concept maybe minima understanding is that H hat explain the contribution is a leverage of each data point on the regression line. Okay? So in terms of computation, it's not so difficult. First, you need to get epsilon z, right? You need to get epsilon z, but you have to adjust your epsilon z. So you need to make a modified epsilon z so that all the Ej follow this distribution. So it's already standardized. Okay, so Ej is standardized. Okay, it's standardized. After standardized that, it's very easy for the B number of bootstrap for all the data from x1, x2, x3, all the data you choose, and then you decide yi, and then you randomly draw bootstrap randomly draw from your epsilon, from the modified procedure, and make it the yij start, that's bootstrap sample. Even xj, you get a yj paired yj sample. Okay? And then you fit the regression and repeat again. B times. Okay. You get your bootstrap beta 1, and then you get confidence interval beta 1 using the BCA, BC, whatever, the best. Okay? So this is I explain this because this is a very common question that encountered by many graduate students. Okay? So if you typically if you do not typically in the typical sense, the regression line is not so good. Okay, and then you bootstrap from your original sample because of the limited combination of your original sample. Usually you count the interval beta 1 is super large, which then make all the statistics impossible to be significant using bootstrap, using the simple paired sample bootstrap. Okay, if that is the case, you have to evaluate your data, and this is better. Okay, this is a better way. Is the confidence interval from the bootstrap residual is a better, more efficient way. Is a more efficient way to calculate the confidence interval of a regression coefficient. Okay, all right. This is not in your homework, but keep in mind that if in the future you encounter a difficulty in your data analysis, you can come back and try to figure out. Okay, or you can ask me. It's okay. Bootstrap residual or regression, very useful, very useful. Okay, second topic, final topic before we end this class. And earlier, we talked about now I'm talking about something called a block bootstrap. Block bootstrap. Again, this is not in your homework, but it's very useful for research. Suppose we have time series data. Suppose we have a time series data, right? And then we have maybe say we are interested in species, 2 species, and whether they are correlated in abundance. So I go out every day and get data for some species, right? And then I find the data like that. Species 1. get the data from maybe species 2. Okay? And I'm asked whether the two species are correlated. I make a regression, right? Again, this is maybe Y, and this is maybe X. I make a regression of these two data points. Now everybody understands that how to make regression, or I'm doing very good, I'm doing the residual regression. Right, very good to do the bootstrap. And I call it a confidence interval. However, this is time series. This is time series. So all the data points, they are not independent, right? Remember, regression, we have to sample independent IID from the real world situation, right? So every data point is independent. So my confidence, my degree of freedom is a n minus 2, right? In a regression, because one used for a regression line. So my degree of freedom n minus 2. But degree of freedom in a regression, degree of freedom is equal to n minus 2, right? N minus 1 minus 1. But the log n have to assume the data independent, right? Data independent. So that's your degree of freedom. If data is not independent, of course, that degree of freedom is overestimated because today is very similar to tomorrow. The population do not change so fast. So it is almost the same as previous state. Of course, in another species, almost the same as previous state. But the degree of freedom is much smaller than n minus 2, right? So when you calculate beta 1, in the very fundamental Gaussian distribution, you have some high degree of freedom, right? And then you check whether beta 1 is significantly different from 0 or not, right? And the degree of freedom is a minus 2 in the F test. But actually, degree of freedom should be much smaller. And of course, the simple solution is adjust degree of freedom, make it n minus, make it effective. Make some way to solve the issue is that I calculate effective degree of freedom. Make a log n star, and then plug in that formula. Right? How can you get n star? N star is related to the correlation function here. If the correlation function is very large, you can, of course, you can calculate today, tomorrow, and so on and so forth. Right? You can calculate the time lag correlation. Right? You can calculate the correlation between today and tomorrow, because at the many days tomorrow, and then you can calculate correlation between the adjacent dates. Okay, it's called autocorrelation. In time. Right, for Y with autocorrelation in time, and Xi with autocorrelation in time. Right, if autocorrelation is large, which means today is very similar to tomorrow, the effect degree of freedom should be much smaller than n minus 2, right? If the autocorrelation is zero, then effective degree of freedom is n minus 2, right? Because it's autocorrelation is 0, which means that every data point is independent. Okay? There are certain ways you can look at literature. There are some way you can calculate effective degree of freedom and make adjustments of your hypothesis test. Okay? And if in fact this is smaller than that, of course, confidence interval will make it larger, right? Because confidence interval is related to the square root of n, right? And that n should be n star because it should be effective degree of freedom. Okay? But today I'm going to explain a better way to do that. Now, instead of figure out the effective degree of freedom, I'm going to estimate the confidence interval of that regression using bootstrap in a more reasonable way, considering the time-dependent structure. Okay, time-dependent structure. So that's from a very simple subsampling theory I talked about last week. Subsampling. So the bootstrap, I sample independently, right? All the data independently, I can sample. However, I can sample this way. I can make a block, sample a block. Right? If I sample this way, subsample this way, then the auto-correlation structure are incorporated in that block. Right? And now I can make many blocks. So instead of sample independent data, I'm going to sample the block. Okay? I'm going to sample the block. Eventually, all the blocks put together like almost the same. It's basically you have to make it the same as the sample size here, right? So you have many blocks. A block that you can block here. You can make a discrete block, or you can make it like overlap block. There are different ways, but that's a technical issue. But in any way, we have a block, Then I can sample block and put together block and make it the same length. I make a bootstrap. Right. Then the confidence interval calculated from the block bootstrap is a reliable confidence interval, right? Because that bootstrap sample already incorporates the auto-correlation structure in that bootstrap process. It's cool? So this is invented by Dimitri Politis from the concept of subsampling. So I talk about subsampling, and subsampling is difficult to understand, but subsampling, bring a lot of spirit, bring a lot of good idea to solve the structural problem, structural dependency problem of your data set. I talk about time, but you can imagine that could be space. But space is more complicated. You have 2 dimensions, then you have to make, that block slightly more complicated. Okay, this block is 2 dimensions. In this case, the time series block is 1 dimension. And then your question is then, how do you decide a block? The block depending on autocorrelation function. If the autocorrelation is large, block is longer. If this is small, the block is small. Right? Okay. And I'm not going to talk about how you decide the block size. Okay, that is explained. That is explained in this paper. Okay, explained in the paper. If you're interested, and then provide a formula, and provide code. Okay, provide code. How do you decide block? How do you decide block length? Okay, block length. Okay, here block length is k. Okay, choosing k is tricky. Okay. So this is sort of subsampling and piece them together. Okay, this is no longer simple bootstrap. Right? This becomes subsampling because now every time I have to choose subsample your data. Okay, but that size of subsample need to be wisely chosen according to the autocorrelation in your data set. Okay, and you make a stick together. Okay, it's called a block bootstrap. Okay, with the block bootstrap, you consider the autocorrelation structure in your data, and then your confidence interval to be reliable. Okay. Okay, with that, more. So Professor Dimitri Politis, then later on, think about a different approach. They say, okay, if I make a block, and eventually there are limited number of blocks you can choose, right? There are only limited combination of blocks because block needs consecutive, usually cheap, right? So there's limited number of blocks you can choose. So there's limited combination you can create from the bootstrap sample, create your block bootstrap sample. And because of the discreteness of your data, the limitation of time series length and discrete nature of this block, they create the distribution of your beta 1, not smooth. Okay, not smooth. So this is good to resolve the issue of autocorrelation, but not efficient because the block create limited combination of potential sample you can choose from. Okay? So how to resolve this issue? So Dimitri proposed something called a stationary bootstrap. Stationary bootstrap. Okay, how do you do a stationary bootstrap? Instead of decide block and choosing block, so what stationary bootstrap is doing is that like that. So I'm going to randomly choose here, randomly choose as the first step. Okay, and then there's a certain probability. I'm going to choose the next one, next one, next one, next one. Okay, and then there's a certain probability. I'm going to jump maybe here, and then the next one, next one, next one, next one, and I jump, and next one, next one, next one. Okay, and then maybe I choose and next one, and quickly jump, next one, next one, next one, next one. So they create another combination, another potential combination, the randomness. And then the question is, how do you decide you are going to choose next one or you jump? Now we understand, if the probability, if the autocorrelation is large, there's higher probability you choose next one. Right? And if the autocorrelation is small, then the higher probability always jump. There's more probability jump. Okay? If the autocorrelation is strong in your original data, there's higher probability you choose next one. If you continue to choose this one, of course this is block. Right? So there's a somewhere in between. So there's a randomness from bootstrap, but the block concept preserved. It's called stationary bootstrap. Okay? And how do you decide the probability to choose next one? Again, depending on your autocorrelation structure. Okay, if this is large, higher probability to choose next one. Okay, that's basically explained here. Okay? So then you create a lot of random bootstrap sample. And unlikely to repeat. Unlikely to repeat. If you choose block, very likely you have to repeat the same combination. Yeah, but if you do the stationary bootstrap, very unlikely you have to repeat sample. So all the bootstrap, stationary bootstrap sample are all very looks very different. Okay, but still you preserved the autocorrelation structure in your bootstrap sample. As such, your confidence interval is reliable. Okay? So this is a very popular stationary bootstrap. Of course, you can generate stationary bootstrap in two-dimensional in space. But then that become more tricky because two-dimensional, whether x, y is isotropic. Isotropic means the probability of x and y is the same. But if it's not the same, it becomes tricky. Right? So the two-dimensional bootstrap, stationary bootstrap become more difficult to generate. Right? But one-dimensional bootstrap or stationary, this is more or less like a standard bootstrap solution for time series analysis for regression question. Okay? So again, in your research, when you encounter your time series data, then I recommend this is the best solution. Okay? This does not have to require assumption of your Gaussian distribution, and that does not require assumption how to make it effective degree of freedom. Right? Without any assumption, you just need to do that bootstrap in a way, consider your correlation structure. Okay, so this is not so difficult to program. Okay, but already someone will do that for you. Oops. Okay, so I think he is still in UCSD, and then he has a website. If this does not exist, you can Google his name. Okay, Google his name. So he is an expert of subsampling and bootstrap. And in his website, he has many MATLAB, R, Python, package you can download. Okay, to do a lot of things. Alright? Okay, so when I was a student in USD, I took a class and then all this kind of bootstrap approach. Right? And then also, if you're interested in bootstrap, this is a good textbook. I think that they have a newer version. So Davidson and Hinckley bootstrap method, their application is a good textbook. Explain more complicated structural bootstrap. Okay, if the data has structure, you have to bootstrap the data following certain structure and then recommendation. Also it is. Okay. Question for today. If not, we'll stop here. Okay, I'll see you next week. Next week we'll talk about permutation, randomization test. We will start very slightly early today.